A very warm welcome to all of you to the Support Vectors Weekly Research Paper Reading. Today we have a distinguished speaker. We have Muppalla Sridhar. He has had a distinguished career in systems engineering. He has worked, amongst other places, at where I used to work, namely Oracle, and he'll tell you a little bit more about himself. He has been actively engaged with research, especially at the hardware level, and it's really we are very thankful that he has volunteered to present today. So with those words, I will now yield to Muppalla Sridhar.
Yeah, thank you, Asif, for giving me opportunity to present at Support Vectors weekly technical paper reading. So yeah, this is Muppalla Sridhar. Today I'll be presenting on the paper like Fastrack, Fast I/O for secure machine learning using GPU Ts. So agenda for today's presentation, I'll be introducing on this paper, giving a brief overview, and then like the baseline will be covered, like what exactly was done in terms of improving the performance on GPU, like cutting down the latency, like what I think what was the baseline that was used to set up, and then like what were the things that were done by the folks who worked on this paper, like what were the key things that they looked at to cut down the latency. So there were three things that they have identified, like those things will be covered in the fast track design. And like in the evaluation section, I'll be providing the results that were collected and like what kind of improvement that was seen. And towards the end, like the conclusion, like what has been achieved by working in this paper. Okay. If you have any questions, please give me buzz, like just interrupt me. I'll be open to answer your questions. Okay. Or you can wait till the end of the presentation and you can ask the questions. Just 1 minute. Yeah, source of the content, like the whole, like the content of this presentation has been borrowed from the paper. The link is posted here in the slide. And this paper was published by the PhD students from University of Southern California. You see the authors, Yongquin, Rachit, Jongbin, and Ting Tang, and all these four USC PhD students have worked on this project under the guidance of Professor Dr. Murli Annavaram. The interesting thing about this paper is like these PhD students, all these four students, they spent almost 9 months to come up with this beautiful and excellent paper. So overall, like they spent 3,000 hours to work on this paper. Okay. And like, I'll be using some of these terminologies like in today's presentation. The TE, it stands for Trusted Execution Environment. So I think like folks who have worked in the server side, like initially like the CPUs were regular CPUs, but later the trusted part came into picture. So the CPUTs have been in existence for the last 10 years. So what exactly the TE offers? Like it provides an enclave, a secure area within the microprocessor, where like you will end up uh, storing the data in a secure way, as well as the code as well as the data are in this enclave location. Okay, so the processor will execute stuff, but I think no other process can access this TE enclave, the TE enclave. Okay. As part of this project, USC has used the CPU T, okay, and like they have used Intel Xeon Gold 6548Y processor, and GPU T they have used the NVIDIA H100 T. This is from the Hopper architecture. So the GPU Ts, like they are also called like GPU confidential computing, and uh, NVIDIA has been providing the GPU confidential computing from the Hopper architecture, and also they are providing the same features, the T features in the Blackwell architecture also. Prior to the Hopper architecture, like the GPUs which came like A100, A2s, and all this stuff, they don't have the GPU confidential computing. The GPT features are not there. Why this is becoming an important right now? There are a lot of use cases where like the customers want end-to-end security. Okay, not only like the network security is provided, which has been there like through TLS protocols and all that stuff, but like within the microprocessor, they want it to be secure. So without using the T feature, anyone can hack into a server and they can sniff whatever information is there in the memory location, the DRAM. They can look into the stuff, the content which is available, and they can, yeah, some PI information can be stored in the regular DRAM. So all that stuff can be avoided, like if T features are used. Okay, in the T features, like anytime like the data is stored, like it is in a enclave secure location, no one can access except for the application which has been authorized to access that location. Otherwise, no other guys can, no other processes can access, can access that enclave. Okay, and the other one is like the paper the students have used AES-GCM algorithm to encrypt and decrypt. So AES stands for Advanced Encryption Standard, and like they have picked up like the 256-bit. Using the 256-bit, like it's impossible for someone to hack. Okay, any data that is encrypted with the AES 256, there is no way current generation uh, computers cannot like hack. Okay, and like apart from the encryption and decryption which this AES offers, it also provides authentication, and like those are kind of like covered in the Mac and AAD stuff. Okay. So introduction, like as I was telling, that customers' request has been to secure the entire like the workflow end to end, like from a user to all the way to the server, within the server, like both CPU and GPU. So if you look at this diagram, there are two major components. We have like one remote user, so it's a laptop that is being used, laptop, desktop. Okay, and then we have a cloud server, and within the cloud server there are two subcomponents. One is a CPU-T and the other one is a GPU-T. Okay, so GPU-T is the one like which takes care of performing the vector calculations or the matrix multiplications, which are very popular in usage, like for training the foundation models. Okay, so, so like in this diagram, like what you see is a remote user is connected to a CPT by using a shared key. Here you see the blue color. So this key is shared between the remote user and the CPT. So, and like there is a process which is running on the CPT. That's the one which will end up using this shared key. Okay. And there is another shared key which is yellow in color. And this shared key is used to secure the communication between the CPU-T and GPU-T. Okay. So there are two keys that you are seeing in this diagram. One, the blue key that is used for communication between the remote user and the CPU-T, and the yellow key that is shared between the CPU-T and GPU-T. And like the enclave that I was talking about, like within CPU-T, there is a area within the DRAM. Like there is a specific area where like no one can touch except for the approved applications only. Okay. And there will be a GPU driver which will be running within the CPU-T. That's the one which will be communicating with the GPU-T. And one more thing. So like if you look at like the GPU world, so there is a humongous amount of demand from these foundation model companies, and also the other companies are also like other enterprise customers are also launching features on their product line, which are like chatbot type of applications. So all of them require humongous amount of GPU resources. One thing that is happening in the industry is the GPU usage in general is less than 20%. So folks are not able to take advantage of all the GPU cores, the CUDA cores and the tensor cores that are available in the GPU. They're not able to take advantage of all of them. So there is a lot of work involved now to make sure like the GPUs are efficiently used. Okay, so like if you look back like 20 25 years back, back then like when I was working at Sun Microsystems, so Sun was dominating the dot-com boom where all the e-commerce companies were buying Sun servers. But in those days, the single physical server was running only single physical OS. And back then also only 20% of the CPU resources were used. Rest of them were just like not being used. So I had like few years later, like VMware came into picture. They came up with this virtualization. They told that hey, like instead of just running one OS on one physical server using just only 20%, so we have come up with a virtualization where like we'll end up uh, creating multiple VMs. Like if we have 4 VMs, so we'll end up using 80% of the CPU on the physical server, and like 20% of the CPU usage can be left for buffers. Okay, if any spike happens in any of these 4 VMs, like they can use the buffer resources that are available from the CPU. Okay, but the industry as of now, like they have settled with 60%. They think that if using VMs, if 60% of the CPUs are used, that's a great achievement. Okay. Now, like the reason why I'm bringing that stuff is the same thing is popping up in GPU. Right now, we are only using 15 to 20% of the GPU resources. Rest of them are just sitting idle. And some of these GPUs are so expensive. The high-end ones, the H100s, H200s, they are like $40,000. So like you pay like $40,000 and use only 20% of it. Uh, I think a lot of work needs to be done to make it efficient. So yeah, there are like new features that are coming up in this area, like MIG feature, like that is being released by NVIDIA H100. So where you can do the hardware slicing of the GPU resources, where each hardware sliced one can be mapped to a tenant. Okay, and they also came up with vGPU, where like multiple VMs can share the GPU resources which are available. Okay, but on top of this, there are a lot of other things. So this paper talks about how to cut down the latency when like the CPU Ts and GPU Ts are used. Okay, so if you have any questions, just let me know. So this is the inference slide. So I'll go more in detail. Like it is still the same diagram that I covered in the previous slide. So we have a remote user and then we have a cloud server. So we have a user laptop or a desktop, okay, which is communicating with the CPU-T, and the CPU-T is communicating with GPU-T. These are using the LO key, and the remote user to cloud, the server, like where the CPT is running, it is using the blue key. So what exactly happens under the hood? Okay, let's take the case of all of us, like we use Chat GPT or like Perplexity, or like we use Claude. So like all this chatbot type of, or Gemini. Okay, so like we issue a prompt, and the prompt request uh, is sent to the server. Okay, but prior to sending the prompt request, first thing is this laptop has to establish a secure secure channel. So first it establishes the TCP three-way handshake with the server. Okay, and once the TCP connection is established, so it'll issue a TLS handshake, and in the TLS handshake, that's when like the process which is running here on the server uh, uh, will communicate with the remote server. They will be sharing uh, uh, a key that is shared. This is how after the TLS handshake, you'll end up having a shared key, the blue key. Each, like both of them will end up having the same key, like the CPU as well as the remote user. So they can use Diffie-Hellman algorithm, or like a private public key. One of these things can be used to generate the shared key. Okay. And similarly, like behind the scenes, the CPUT and GPT, they will establish a secure channel, and they will end up using a shared key, this yellow key that will be established. Okay. So let's go back to this one. Like now, after the TCP connection being established, followed by TLS handshake, so the prompt request, that is the prompt request that is sent by the user, it will reach the CPT. But I think it will be encrypted. That prompt request will be encrypted, and it will reach the CPT process, and the CPT process will decrypt uh, the received message, and then like it will, along with that, like there will be a MAC information that will be submitted by the end user. So it will check like the received data is not tampered. So as long as the MAC value that it receives matches with the MAC calculation it does with the uh, decrypted data, if they match, like then it moves to the next stage. So in the next stage, like what it does is it uh, encrypts the data that has been decrypted with the yellow key, and then it sends it to the GPT, and the GPT will decrypt with this yellow key, and also like the MAC that was submitted by the CPT, it just verifies after decrypting, just to see like there is no tampering involved, and like then like it goes ahead and runs uh, basically the prompt request will be running on the foundation model, which is running on the GPU-T. Okay, so once the operation is completed, so the resulting data, the output, is again encrypted by the GPU with the yellow shade key, and it will send back to the CPT. CPT will receive the data, and like it will decrypt it, and then also it checks whether the MAC value that was passed by the GPT is not tampered. Okay, so as long as it is not tampered, so it goes ahead with the next step. After decrypting, it again encrypts the data with the blue key, and also generates a MAC value, and sends it to the end user. And the end user will decrypt with the blue key and check like the MAC value it received is matching with the MAC value of the received data, basically the output for the prompt request. Okay, and then like if everything is good, and like that output gets displayed on the user's screen. Okay, so do you have any questions on this? Okay, let me. So these are the steps that I just described. And this is a training. In the training, the assumption is the data is already uploaded into the CPU T, and all it does is it encrypts with the yellow key that is shared with the GPT, and also it generates the MAC value with the data that it is trying to encrypt, and then it sends it to the peer, like in this case the GPT. The GPT decrypts it, and then takes care of uh, checking the MAC value that it generated from the received data, which is decrypted data, and checks like whether the received MAC value is matching with the computed MAC value. If they are all same, then it goes ahead and does training related operation on the GPUT. So where the matrix multiplications, all that stuff happens in the training of the model. Okay. Any questions on this? So this is a description of the steps that was discussed in the previous diagram. So the baseline. So in this diagram, you see the plain text, okay, and then you see the nonce, which is a unique number, plus they add 0. So what they have done is this: the data is being encrypted. So the way the encryption happens is unique value, a number is generated, and it is fed to this AES. AES, as I was mentioning, it takes care of doing the encryption and all that. So it's the same key, the shared key in all of this, okay? The shared key and the nonce, and then it does operation which will result in key stream where bits of random bits are generated, and this is the one which will be uh, 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 exclusive OR with the plain text data, and then the resulting is a ciphertext. Okay, it is a cryptic output. Okay, there is no way someone can get access to this and generate the plain text. They don't have access to the shared key. Okay, it's very difficult to get access to the shared key. Okay, that's what is happening. Even in the decryption case, you'll end up using the same shared key, and the the random bits that are generated, they are exclusive OR with the ciphertext, and that's when you get back the original plain text. So the same shared key will be used to decrypt the ciphertext, but some additional operations are done. Okay. So this particular operations, you see these can be parallelized. There is no sequential related stuff. The chunks of data, each chunk of the data, you generate a corresponding uh, encrypted data that we call it as ciphertext. When it comes to the MAC, so there is here you see there is sequential related operation. So you see the ciphertext 0, 1 all the way up to M. Okay, it is fed to this one, and the subkey H is used, same subkey H, and there is a AD some unique value that is exclusive OR with the output of the last uh, subkey operation with the ciphertext, and then it is fed here, and there is an exclusive OR with random value that is generated. Through this, you get the MAC tag. Okay, so this is a sequential operation. Okay, so the university students and the professor have looked at how they can make it more efficient. Okay. So for the baseline computation and communication flow in the inferencing, first the CPU T, what it does is it, as I mentioned in the one of the previous slide, it does a decryption and then verify the auth. Here is nothing but the MAC value. Does it whatever the MAC value is there that is received from the peer? In this case, the user provided the MAC value is matching with the MAC value that is calculated by the CPU T. Okay, if they are matching, then it goes ahead and encrypts the data. Also, like it generates the MAC with the plain text and then sends it on the PCI bus. Okay, and the PCI bus will hand it over to the GPU-T, and then the GPT first it does the decryption, and then like it again the MAC related values it tries to verify they are matching with the auth value or authorization value, which is nothing but the MAC. So calculated value versus the received value, if they're matching, then it will go and do the inferencing related operation. Okay, and like once inferencing operation is done, like again like there will be MAC value that is calculated, and then encrypts the data, sends it to the CPU-T. The CPU-T decrypts it, and then does MAC value calculation and compares with the MAC value received from the peer. And if everything is good, then it takes care of encrypting the data and like sends it to the peer. Apart from encrypting, it also calculates the MAC of the decrypted data that it received. Okay. So with respect to training, so here like we see like it does encryption and the MAC generation, and that is sent to the GPT. GPT like decrypts it, and again it tries to verify there is no tampering that is done. The MAC value it receives from the CPUT is compared against the MAC it generates by doing the operation on the decrypted data. And once they're matching, then it goes and starts uh, doing the training operation. Once the training operation is done for that particular workload, it again like encrypts it, uh, creates a MAC value of the plain text and sends it to the CPUT, and CPUT will take care of uh, decrypting it and then like checking the MAC value that it received is matching with the MAC value it generates from the uh, decrypted data. And that's the main thing that happens in the training operation. Any questions on this? So like USC has used three models as part of this paper submission. They have used ResNet 50. So they have used the ImageNet dataset, like it's a massive dataset consisting of 14 million images. Okay, and they also use the GraphSage graph convolution model, and like for that, like they use the OGBDN products dataset. It's a popular benchmark for node property prediction tasks in the graph neural networks. And the third model is the two tower neural network. It's popular for recommendation systems. So movie lens 1 million data set. So yeah, it's yeah, I think like if you guys have played with the recommendation system, most probably you would have used the movie lens 1 million data set. So they have like 1 million ratings from 6,000 users on those 4,000 movies. So this is a table in which they provide like how much time it takes to do the data transfer per batch. CC stands for confidential computing. So NVIDIA confidential computing, and like when they were not using like non-confidential computing, it's a plain. Okay, so three models, and like here you see no GPU T. So for ResNet, it takes 312 microseconds to do the data transfer. It's not like doing any number crunching or anything like that on the GPT, just purely data transfer, how much time it takes. NVIDIA confidential computing, it takes like 3.96 milliseconds. Okay, and NVIDIA CC inferencing one, it takes 6.41 milliseconds. Now, the second table is the total execution time. Okay. And let's compare So if you look at the ResNet 50, 35.84 milliseconds is the total execution time. Okay. And now compare that with the data transfer. It's just 312.5 microsecond. See, significant amount of time is spent on GPUs, okay, processing the data. So yeah, I think like the paper focuses on like how to cut down the time. So let's see like how much they are able to cut down the latency using the ResNet. So same thing like here you see NVIDIA CC compared with NVIDIA CC training. So here 3.96 milliseconds, almost 4 milliseconds. Out of that, like I think like the total time is 39.49 millisecond. So here like you see like 35 milliseconds is used for processing. Only 4 milliseconds, close to 4 milliseconds are spent for the data transfer. And if you compare this one, like NVIDIA CC inferencing, the 6.41 milliseconds. So with the NVIDIA confidential computing, it's 17.37 milliseconds. Okay. So yeah, so I think like there is a good chunk, almost like 1/3 of time is spent in the data transfer. But compared to the, let's look at the other two models, Graphs, Sage and TTDN. Okay, here you see like 2.1 milliseconds is spent for no GPU T and 8.66 milliseconds. If you look at uh, the TTNM for the no GPU T, 2.19 milliseconds compared to 35. So here, yeah, so like less time is spent, I think, in the data transfer. Yeah, and like here, like good amount of processing is involved. So if you look at this one, like this is an interesting one, NVIDIA CC. Okay, 51.43 milliseconds is spent on the data transfer. Okay, and you look at 84. So almost like 2/3 of the time is spent on the data transfer. So there is an opportunity to reduce this significantly. Okay. So here also you see 32.6 milliseconds for the graph stage and like 39.16. So like almost like 80% of the time is spent on the data transfer using the NVIDIA CC. If you look at the NVIDIA CC inferencing, same stuff, 45.5 milliseconds for the data transfer and 48.9 milliseconds the total. So there is a huge opportunity to reduce this one also. And same thing, 73.45 milliseconds for TTNL and like 84.79 milliseconds. Okay, so this is interesting data point that they were able to collect. This is for the baseline. Any questions you have? So let's look at the design that they have come up with, like to cut down the latency. So first thing what they have done is like they looked at, I think if you look at this diagram, the remote user, the cloud server. So I think in this, what you have seen is like in the previous diagram, there are two keys used. Okay, one is between the remote user and the CPUT, the blue key, and then like they have used the yellow key between the CPUT and GPUT. Okay, so so you are seeing like in the transmit path. So there was one encryption done at the user, and there is one decryption, there is another encryption, and there is another decryption. So in the transmit path itself, you have two encryptions and two decryptions, and like MAC calculation two times. Okay, so there is an inefficiency. Even in the reverse path, also same thing: two encryption, two decryption. What they have done is like they decided not to do any decryption and encryption in the CPUT. So they have come up with a direct communication. So the remote user will directly communicate with the GPU-T. Okay, so that is so by using this, so the red, like in this case, like the red key is the one that is shared between the GPT and the remote user. Okay, so with this approach, you will see only one encryption at the source, and the decryption is done in the GPT, and and then again like GPT does encryption of the resulting data and sends it back to the remote user. Again, like this communication will go through CPUT. So what happens in this case is whenever the encrypted data comes to the CPUT, it knows that the key that has been used for encrypting is the key that is generated by the GPT, and like it just passes through. Okay, and same thing like the resulting data before, I think once the GPT receives it, it decrypts it and it does processing and then again encrypts the process data and sends it to the CPUT. And CPUT doesn't do anything; it just passes through. It knows that okay, the key is already shared between the remote user and the GPT. It just forwards the packet to remote user. Okay, so they got like very good reduction in the latency. I'll show you in upcoming slides. Okay. So this is one method that they have used to cut down the latency. Okay. Any questions on this slide?
So basically, I'm trying to understand why they are having a separate security for CPU as well as GPU inside the cloud server. Are these shared resources or how it is?
No, see, like some hacker can get into the CPU
Mm-hmm.
and he can sniff the traffic if this is not secure. Okay. So in the secure world, like they want like everything to be secure end to end. So see like the memory where like see after decrypting the data, okay, let's say we are not using CPUT, so the CPU does the decryption like I think with the blue key, and once it is decrypted it will be in a memory location, and like if sophisticated hacker uses a tool which scrapes through the memory location where like all this content is stored. Okay, so they get access to all the data that has been decrypted.
But once he gets access to the CPU, he is already in the tenancy, right?
Yeah,
Once he is in the tenancy, he should be having access to GPU also in that
yeah,
case.
GPU access. Yeah, it's like if the T feature is not used, he can scan the memory. But like once the T is there, uh, hacker who gets in, he doesn't have access to the enclave location where the data is located. The code that is executed and the decrypted data that is stored in the DRAM, okay, in the memory location, the enclave location, the hacker will not have access to it. Okay, so it'll if he tries to access, it will say denied. Like you don't because the user will not have access to that. Only approved application only will have access to that uh, data.
Thank you.
So GPT also has memory. Okay, there also they have an enclave. So they are protecting uh, that memory where like they will be storing the decrypted data. Okay, so no one can access that part. So did I answer your question?
Yeah, I'm some sort of, but still there are a lot of loopholes here. That's what I was thinking. Yeah.
No, there are no loopholes. There is nothing like uh, the data. See, once see like all this, the processing and the storing of data is all like in an enclave. Okay, you can think of it as a VM running in a secure way. So there is no way like people can get into that.
Okay.
Yeah. So the hacker cannot get it because like it's very there is no way they can hack into that enclave location. They cannot scan. It'll all be cryptic information because
Okay.
like yeah. So because like that's secret sauce of the tea. Okay.
Yeah.
Any
Thank you.
other questions? Yeah. Any other questions you guys have? So the server communication flow, yeah, this is what like I just explained. Like I think the secure communication to GPT, like the PC transfer, is all like secure, and the decryption. It's like there is an enclave in the GPU side also. So that's a place where like the mm, the kernel code as well as the the decrypted data is all stored. So it's all like protected. So the second thing like they found out was uh, mm, improving by using the multi-chaining. Okay, they have decided to chunk, because like if you go back the Mac here, so the Mac generation, it's a sequential operation. Okay, so there is no parallelism there. So to create parallelism, what they have done is like each image is being split into 16 chunks. In this diagram, it shows only 3 chunks. Okay, so once they split uh, into multiple chunks, each chunk will have some unique number, and it is fed into the GMAC engine. And like they use AES, like nonce is a unique value is created, and then they do exclusive OR with this chained mult with H, and it generates a unique uh, value, and that's what is the tag. This is nothing but the MAC. So you will end up creating how many chunks you have created, that many number of MACs. All this can be executed parallelly on the GPU. Okay, so that's advantage. And the other one is like these chunks can be received by the GPU out of order. So when the decryption is done and all the stuff, it looks at these numbers, like it reorders in the GPU itself. That's the reason they ended up putting it this number. Okay, so the multi-chaining is providing parallelization. The other third one is the server computation flow with all optimization. So what they've done is, if you go back, let me show this. See, like for each plain text, it generates a ciphertext. Okay, so the major chunk of the time it spends is generating this output. Okay, so this is the place where it's at. And like to generate the output of this, like the nonce plus AES, okay, the random bits, okay, it doesn't depend on this plain text. So what they've done is, okay, while the plain text is being transmitted over the PCI bus, during that time, they generate this very expensive operation to generate the bits. So the exclusive operation is less time consuming. So they while the data is being transmitted on the bus, it takes some time. Okay, during this time, they're able to generate the key. Yeah, not the key, the random bits. They call it as key stream. Okay, and that key stream is exclusive OR with the plain text to generate ciphertext. And the reverse is also same thing for converting a ciphertext into plain text. Generating the random bits takes good amount of computation time. So in this diagram, that's what it is saying. The AES, the encrypted data is being transmitted. During this time, it is generating the random bits. And once the data is received, okay, then like it does exclusive OR, either to create a ciphertext if it is received. So basically, like it tries to, in this case, like the GPT will do the decryption. Okay, so the decryption operation will be done like after the data is received. But by this time, it has already completed the decryption operation. Okay. The second one is the auth value. Okay, what they have done is this is a batch one. Okay, where like the data is being transmitted, the computational work is going on, and like once encrypted data is received, like it does the decryption operation. But like after decrypting, you will do the MAC calculation. Okay, so MAC is a sequential operation. So like what was happening was in the past they were doing like all this stuff like in a sequence. Okay, first like they will wait till all the encrypted data is received, then like they were decrypting it. For decrypting they have to generate series of random bits, and like that takes time, and then like they do exclusive R on the ciphertext, then it generates uh, clear text data, and on the clear text then they calculate the MAC, and then the MAC calculated one they'll check with the MAC that they received. Okay, so a lot of sequential related work. What these guys have done is when the batch 2 data is being submitted, okay, so as soon as the batch 1 uh, work, basically this encrypted data is received, when it is doing the exclusive work, like it will hand over the ciphertext to be executed on the GPU cores, CUDA tensor cores, okay, and it will not do the MAC calculation. So MAC calculation, yeah, so it will start doing like after the GPU cores are computing, because it takes time, like the GPU core calculation. During the time, uh, so it does the MAC calculation. So when the MAC calculation is going on, at the time like the second batch of the data is being sent through the PCI bus, and like the second batch related random streams are getting calculated. So in case if the MAC value that is generated for the batch one, okay, does not match with whatever was sent here, then the computational work that is going on with respect to the batch one, it will be dropped. Okay, they will send a message to the peer to send, basically to CPUT to send that data back. So like some kind of parallelism, some kind of like efficiency has been brought in. So instead of waiting for the MAC calculation, so they do while the batch 2 data is being received. So the MAC value is being calculated for the previous batch. Okay. Any questions? So these are the three things that I discussed: direct communication, where we are cutting down the uh, encryption and one decryption, but also the MAC calculation and the multi-chaining. So we are chunking uh, the image, a single image into single 16, maximum 16 chunks, and each so like they have come up with this parallelism, okay, and the decryption pipeline. One is keys, basically the random bits are being generated for the decryption work, okay, and the other one is the MAC calculation is done for the previous batch while the current batch is being transmitted. So with all this stuff, like they got like a very good reduction in latency for these models, the three models. So the evaluation, so here like this is a baseline, like the baseline is when like they were uh, using the T option, but like now see like what is happening is they had to emulate software, like they had to develop their own protocol. So the protocol is like this multi-chaining, they developed their own protocol, okay, and then like this one also, the decryption pipeline was also they did it, and direct communication. So they made changes, they developed their own code by default, like when you use the NVIDIA GPU CC, the GPU driver is the one like which does all this stuff, but it is not efficient. Okay, so to make it efficient, like they have built a user level uh, emulation which takes care of doing all the three things that I discussed. Okay, so without using that, like GPU driver, the one which is running on the CPU T, it does job, but I think you ended up seeing like double encryption, double decryption, 2 times MAC, no parallelism with MAC, and like no efficient usage of the PCI bus. Okay, so all those things like these guys ended up doing it, but this is a baseline without their code. Okay, so the base with their stuff. Okay, so what they have without using the Fastrack implementation. So like how much time it was saying for the GCN, it's this one for inferencing like close to 50 milliseconds. Out of that, yeah. So how much time was spent on? I think like you can see like the CPU decryption authentication is pointing to this one. Yeah, so I think like the blue one, like the CPU encryption authentication, and the yellow one is the PCI transfer. Very small. Okay. ResNet, pretty much, yeah, yellow is pretty much ignorable, but a good chunk of the time is spent in the GPU compute. Okay. And the T tower, yeah, so like I think you see, so close to like 85 milliseconds. In the training, you see close to 40 milliseconds in GCN and like 42, 43 milliseconds for ResNet. And T tower is 80, close to 85 or 84 milliseconds. Okay, so here you see the PCI. This is the yellow one, very small amount percentage compared to the overall. The T tower, the GPU compute is a good chunk. So GPU authentication in the purple one and the blue one, like the CPU encryption and authentication. So this is the one that they collected, like using those three features that they developed, the Fastrack. Okay, so this is a baseline number, the one that I showed in the previous diagram. Okay, but it doesn't dissect like where it is spending and all that, but like overall, like how much time it spent, close to 50 milliseconds. Okay, in the GCN inference, and there is a ResNet inference, T tower inference, and the trainings are all the bottom three diagrams. Okay, these are the bar charts. So here you see like in the GCN inference, it says the DC stands for direct communication. Only when DC, the direct communication feature is enabled, okay, they see like 52.8% reduction, okay, in the latency. So you see like it is able to get the work done in 23 milliseconds compared to 50, okay. And multi-chaining, when they use only multi-chaining option, they get 25.4% reduction from the baseline. Okay. So which is close to 33, 34 milliseconds. And there's a decryption pipeline, they get 12.9% reduction. So it is around like 38 milliseconds or 48 milliseconds. Okay. When they combine this MC plus pi, multi-chaining plus the decryption pipeline, the second and the third feature, they get 31.7% reduction. Okay. And like combining these three main features, DC plus MC plus pi, they get 84.6% in reduction. So it is spending like 7-8 milliseconds compared to the baseline 50. Huge reduction they got using GCN inferencing. Okay. So like now, like if you look at the CC on, where they don't use any of the USC students software, the default one when the GPT and CPT where they use double encryption, double decryption, and like the Mac, no serialization, no efficient usage of PCI bus. So it takes 80 milliseconds, more than like what they have done using their own code. Okay. So now like when the CC is off, okay, when the no security is used, the no T's are used, it is comparable to this one. You see, like now like they have implemented those three features which provide security, like the T features, with comparable numbers with the CC off. So they have done like amazing work. Okay. With respect to GCN, they got like the good reduction. Okay. Same thing you see with T tower. So T tower also, they see like 80 milliseconds. When you combine all these three, DC plus MC plus pi, they are getting 81.7% reduction. Okay. So this is comparable to CC off. Look at the CC on value. This is also close to like 95 milliseconds. So with respect to ResNet, okay, which involves like images, so they got like 31.4% reduction, not like the same kind of stuff, because good amount of time is spent in the GPU computation. So that's why they were able to get up to 31.4%. Okay. Now, when you look at the training, in the training, like you are able to see like 72.5% reduction in the GCM. Okay. And this one, like ResNet, like just only 8%. They got like close to 8% reduction, because in training, like a lot of time is spent in the GPU computation. So they could get only 8%. And like with the T tower, they were able to get like a good reduction. Okay, 55.7%. It's a good one. And this value, the combined value, is comparable to CC off. Here also, this one is also comparable to CC off. Okay. So do you guys have any questions on this diagram? Did you find it to be interesting to use this student developed feature? It is not publicly available right now. Hopefully they will be releasing. And like NVIDIA, I'm hoping that NVIDIA will look at this paper and like they can make all these improvements in the GPU driver.
I have one question, Sridhar.
Yeah.
Chandra here. What is the difference between the baseline and the CC on?
Yeah, so baseline is their code, okay? The code that they did to implement the same thing, whatever the double encryption, double decryption, the MAC. So it does the same functionality as the CCR, but it will not use the GPU driver. In this case, NVIDIA GPU driver is getting involved to do the decryption and encryption. Basically, the shared key generation and all that. So
How did they achieve that improvement in baseline compared to CC on? How did
yeah,
they
so
achieve?
there is, yeah, because they developed their own protocol. So I
Okay.
think like they developed their own. The emulation software is better. Like I think like so it is better than like what is being provided by default.
Okay. Thank you.
Yeah. And the improvements are huge. Like when they use the Fastrack. So yeah, this brings back to their stuff. Like only 15% of the GPUs are efficiently used. 15 to 20% only is the usage. So this is one way. Like they have looked into cutting down and using the resources efficiently. Okay. So this is, yeah, I was excited like when I looked at this paper and I saw, yeah, there is an interesting stuff that they did. Yeah, looking forward for NVIDIA guys to come up to make their driver uh, run efficiently, probably like implement the same thing what these guys have done.
Thank
So any
you.
other questions? Yeah, any other questions on this? So the conclusions, yeah, the inefficiency was CPU re-encryption, like double encryption, double decryption, lack of parallelism in the MAC, verification, and like the operation like serialization. Okay, it was serializing like it was one by one, like it was executing all the steps. Okay, it expects the data to be received by the GPU, and then it does the decryption, and then like it calculates the MAC. Okay, and after all this stuff, verification MAC is correct with the calculated work, then it hands over the work uh, to the GPU cores to do the training or inferencing work. So they have cut down like by using the decryption pipeline. And then the multi-chaining authentication, chunking the single image to 16 up to 16 chunks. So that's another second useful feature that they develop. And the first one is the direct communication link with GPUs. So these are the three things that they have done. Any questions? And like if you guys want to look at the paper is available. So all the diagrams that I have used, they are from the paper. Pretty much like the paper that discusses, those are the ones that I covered in the presentation. Direct communication with GPU, multi-chaining, decryption pipeline. And as I told you, like, they are using the H100 from NVIDIA. Okay. And there are a lot of references towards the end of this technical paper. Any other questions you guys have? I think you can work on like the next generation if you guys have access to D100. So you can work with the students and collect the numbers, how it looks like on the D100.
Right.
Yeah. So that's all I have for today. And again, I want to thank Asif for giving me the opportunity to present today's technical paper reading. Thank you.